guys ready for more linear algebra?
Yeah.
All right. So today we're going to do what standard linear algebra courses more or less start with, which is the mechanics of matrix manipulation to solve systems of linear equations. And then on Monday we'll sort of get some perspective on what's going on and introduce some terms. We'll have a fair amount of vocabulary about certain kinds of linear systems, whether you can solve them or not, how many solutions you expect them to have, and so forth. So I wanted to start with an example. Now, before I do that, so if I wanted to look at a system of linear equations, what does it mean that it's a system? Well, typically it means that there's more than one equation. What does linear mean? All the variables appear linearly. And so you might have something which in abstract notation would have coefficients in it, and this looks remarkably like matrix multiplication notation, right? So you could imagine that each equation has its coefficients which are numbered with a different first subscript, and so on. And what you recognize is that we can write this very succinctly as a matrix equation. And we already did a little bit of this stuff even back in chapter 1. So you can write this system of equations much more handily as AX equals B, where A is the m by n matrix that has all the coefficients of the x's. Right, so you have aij's, I here is going from 1 to m. So the I variable is the first one that says which equation I'm looking at, and the j's are going from 1 to n, corresponding to the n variables. Now, so let's just do an example. And I'm going to purposely leave some room, so if you're actually being silly about this and taking notes, you might want to leave some room in your notes. So I'm going to, rather than using subscripts just because you get tired of writing them, I'm going to just use x and y here. So I'm going to use m and n both being 2. And I'm going to write down, for this stuff I do have to cheat and prepare ahead of time, because otherwise the numbers turn into horrors. If you just sit down with your friends and say, let me show you a random system of equations and make up numbers, you can probably imagine it's going to turn horrendous. So this is one place where I actually do try to make stuff up ahead of time. Okay, so there's a system of equations. What I wanted, you all know how to solve this. Back to 7th grade, you probably knew how to solve this. But I want to do it in a way that's going to be an algorithm for us. So you might think what I'm saying is arbitrary, but by the end you'll believe that it's useful. So my algorithm is going to be try to get rid of one variable at a time in subsequent equations. And for such purposes, I'd rather use this equation to work with to kill off the x term here than vice versa, because I don't really like fractions. I mean, I know you all love fractions, but I would rather avoid them. And in fact, most of the web work problems and most of the test problems I'm going to give you, you will avoid fractions if you're doing it correctly. So that's advice. So the first thing I'm going to do is say I'd rather have this equation first, because then I have a 1 coefficient, and 1s are my friend. So I'm going to switch the order of the equations. that clearly didn't change what the solutions are going to be. I'm going to then use this equation to kill the x's here. So I'll add -2 times this equation, add -2 times the first equation to the second equation. And I'll then have x minus y equals 7, and 2 minus 2 is 0x, y minus -2, 3y equals
15, -15. -15.
So, word of advice, watch out for negatives, especially when you're subtracting. Right, so 1 minus -2 is 3, -1 minus 14 is -15.
Oh, that's pretty.
And then I say to myself, I don't like this equation. It would be much simpler if I had a 1y. So I'm just going to rewrite that second equation as y equals -5. And then I'm going to do the last step, which is to add the y equation to the first equation to kill off the y's there. So I'm going to add the new version of the second equation to the first, and that will remove the y, and I'll be left with my solutions. Y is -5, add this equation to this one, I get x is 2. And if you want to be careful, you go back and you check. Yeah, no, so I'm teaching you an algorithm that is not what you've always done in your life to this point, and that you will see why you want to follow the algorithm. I'm not saying it's the only way of solving, but we can check, right? 4 minus 5 is -1, 2 minus -5 is 7, yeah, it checks. Now, the reason I left space is I want to follow along and realize that I could have done all this stuff without writing the x's and y's. I could have just written the coefficients and then made myself a little column here for the b vector on the right. So for those of you who have never seen this before, you get what the A matrix is. That's the matrix of coefficients. And what I've done here is I've made what's called the augmented matrix, where you take A, put some dotted lines, and you put B on the right. If you're doing this on a computer, of course, you don't put the dotted lines, because it doesn't say, there's not a key for dotted line. You just make an extra column and remember what you're doing. And now what you notice is that all the stuff I did, I can just do with the matrices, and it's always the same equation when I do whatever operation to the matrix. I'm still just saying this matrix times x is this vector. I'm not changing the system of equations any way other than what I wrote down here. So what I can do is I can switch the rows, which is what we did first. Then what did we do next? We added -2 times the first row to the second row. So we recopy the first row, and then you add -2 times it to the second. So I end up with the same stuff I had before. I'm then allowed to take any equation I want and multiply it by a non-zero scalar. So in this case we said let's multiply by a third. And we now had this equation. And then finally we added this row to this row to kill all the -1. And we were left with what matrix here? The identity matrix. So the goal is, when possible, to end up with the identity matrix here, because then you just have the system of equations, identity times x equals something. So what we just did are called row operations. And in this case, we turned it into the equation identity x equals whatever vector c, and we've solved the system of equations. So in general, we're going to do this with non-square matrices. There might be more rows than columns, there might be more columns than rows. There may or may not be, yeah, so let me just make a comment here. Comment, when b equals 0, suppose you put all the right-hand sides equal to the 0. So we're considering the system of equations ax equals 0. We needn't write a column of zeros. Why? Because no matter what I do in terms of these operations, zeros are never going to change. Right? If I switch, they don't change. If I add a multiple of one row to another, zero's getting added to 0. If I scale and multiply it through, it's still 0. So I don't have to bother with the zeros. This, by the way, is called the associated homogeneous. There's that word again, like in Euler's theorem, and it's homogeneous, it's not homogeneous. Don't say that. So if you take the b and you take the equation ax equals b and you turn it into the system ax equals 0, it's called taking the associated homogeneous system. The original one, we'll talk more about these words on Monday. The original is then called inhomogeneous.
It's supposed to be not like other things. The opposite of homogeneous
Is heterogeneous.
Yeah, why is that?
Math is math. Okay, so basically we're playing a game here. And I think what a game. It's not as exciting as Scrabble. Actually, love Scrabble. Don't knock Scrabble.
That's Monopoly.
But rather than telling you the rules of the game, I'm going to do one more example, and then I'll tell you the rules of the game, and you'll see when we're at the end. So here's another example. Someone's ringing.
Sorry, on the line.
So I'm not going to write it all out with x of 1s, x of 2s, x of 3s. I'm just going to write the augmented matrix down, if you'll allow me. I guess I'm going to do it even if you don't allow me. Okay, so this represents a system of 3 equations and 3 variables. And I very kindly put a 1 in the upper left-hand corner to make my life easier. So the game plan is going to be use that 1 to clear out down below it. So I'm going to start, just to keep track of what I'm doing, I'm going to circle that 1 and say, okay, by the way, I'm going to use a squiggly arrow, as does the book. Doesn't mean equals. It means get from here to here by doing row operation. So this symbol means perform 1 or more row operations. And I guess, so let me just keep track. What are the row operations I'm allowed? I'm allowed to switch rows. I'm allowed to
Add some sort of multiple.
I'm allowed to add a multiple of one row to another. And I'm allowed to multiply a row by a non-zero constant scalar. Okay. So some books will belabor this and write down all the steps and indicate exactly what row operations they're doing. I'm certainly not going to ask you to do that, but you do want to make sure you can follow what you did. And next week we're going to see that we'll have a device of doing some bookkeeping, which will be interesting. All right, so we write down the first row as it is. We're going to use this one to kill off below it, and I'm going to do both in one swell swoop. So I'm really doing two separate row operations, but I don't want to write it all out twice, and nor do you. So what's my second row going to be?
0, 2, 4, minus 2. 4, minus 4.
So we're adding -1 times the first row to the second.
4.
Everyone agree? Third row. What am I doing? Adding -2 times the first row to the third. 0. -2 times the first row. So this is -2 plus 6, which is 4. The observer notices what? Bottom two rows are the same. What does that mean?
You can't cancel.
Well, I didn't really have the same equations, but the content of these three equations was redundant. And really,
We only needed.
I only needed 2 equations
Right.
worth. The third gave me no new information, but let's go on one more step anyway.
You won't get them.
So I have 1, 1, 3, 1. What will you allow me at this point to multiply through by? -1/2 even. Because in general, I'm happier with ones than I am with other numbers. So my goal is going to be to turn this number into a 1. So I will have 0, 1, 2, -2, and then adding this row, the negative this row to the third row,
This is 0, 0, 0, 0.
it's 0, 0, 0. 0. So at this point, I have my sitting ducks in a row. So I might as well start using the lingo. These are called pivots. The first non-zero row, the first non-zero entry you get to in a row is called a pivot. And so what I've now got, I'm happy with this because I've got pivots. I've cleared out below them. So I have pivots, which here are ones. And pivot, remember, is the first non-zero entry of a row. And what I've arranged here is that the pivots, first of all, I've cleared out below. The column is cleared out below each pivot. And also what I've arranged here is that the pivots move down and to the right. So you might even say,
No 2 pivots are in the same column.
right, I've cleared out below a pivot, right? So there can't be 2 pivots in the same column. And what I've got here is the beginning of a staircase. So the next comment is pivots move down and to the right. I'm sure you can come up with a pedantic mathematical definition if you really want one. And the last comment is any row of zeros. Of course, it has no pivots, so the rules don't apply to it, but I'm going to make sure that any row of zeros that I happen to have is at the end, is at the bottom. So if there's several rows of zeros, they all go at the bottom. Okay? This matrix is called a matrix in echelon form. I didn't even need the pivots to be ones officially for that. Pivots can be any non-zero number. So if you have a matrix where you have this descending staircase and you cleared out the rows of zeros, put them at the bottom, that's called echelon form. Any French people in the room? Échelle?
Ladder?
Ladder. So I said staircase, but you can all, so
It's ladder.
you could think of it as a ladder, sort of being ladder-ish.
Right.
So this matrix is, using the rules of the game, I've arrived at echelon form. Now for almost everything we want to do, we're going to go one step further and get reduced echelon form. So continuing the green, reduced echelon form has further requirements that the pivots must be 1, which I actually did here out of habit anyway. And what we did in this first example, once you have a pivot, you also go and make sure you've cleared out above it as well. Well, there's nothing to clear here. So entries above pivots cleared out as well. So what's the extra step I have to do here
Have to
to
subtract.
get it reduced?
Subtract the second line from the first.
So I want to use this one to kill this one, so I'm going to add -1 times the second row to the first. First I'll recopy the second row because otherwise I'll screw up. And then I'm going to add -1 times the second row to the first. It does not affect that pivot. Good. 1 minus 1, 0. 3 minus 2, 1 minus -2, 3. So this is now reduced echelon form. Now what I can do, so let me just say, the game we're playing here is using these allowable moves. The goal is, namely you'll win when you arrive at echelon or reduced echelon form, depending on what you want to do. So your goal is arrive at, and for most things we want, you'll see why, reduced echelon form. Can I have the same matrix that I start with and have different echelon forms?
Sure. Yeah.
Sure, especially with this comment I made here. Right? Because I can take scalar multiples of my rows. What do you think about reduced echelon form? No. And that's actually a theorem that we'll prove a little bit later. Reduced echelon form is unique. I'm not very fond of the proof that's in the book, so I'm going to show you a better proof. I was not smart enough at the time the book was written to come up with the best proof. So now there's a better one. Okay. Now we started this story where we wanted to solve a system of equations. So this represented a system of equations that I wanted to solve. How do I now read off the solution from this? So what I want to show you how to do is giving the solution in standard form. So when there's a reference in the book or in web work to give the solution or the general solution in standard form, here's what is intended. So my original equation we've agreed is equivalent to this equation, because nothing I did changed solutions. My final form now says x1 plus no x2s plus x3 equals what?
3.
And the second equation is?
X2 plus 2x3.
2x.
Equals. So here's what I want you to do. And again, it's an algorithm. I'm not saying there aren't other ways to write the solution, but this is how I want you to do it. Take your pivot slots. So I'm going to call these guys the pivot variables. The variables who are left over, in this case only x3, it's called a free variable. So it's going to be a parameter that we're going to allow to vary freely, and its values will determine the values of the pivot variables. So it's like doing parametric equations. So what I want to do is I want to rewrite this, solving for the pivot variables. And I'll get x1 is 3 minus x3. And x2 is -2 minus 2x3. And then the next step, and if you skip this step, you will screw up, so don't skip this step. Now, you could have combined this step with this, but you should have this written down. So you have a column of constants, and then you have a column with the free variable in it. And if you had had more free variables, there'd be columns with other free variables as well. Now put this in vector form. So the solution, vector x, can be written as a vector with only scalars in it, plus a vector that has x3, the free variable, in front of it, and what are the coefficients?
-1, -2, 1.
So you now recognize this from chapter 1 as parametric equations for a line. A point plus a scalar times a direction vector. Single direction vector, so it's a line. Now if I had more free variables, I would get a plane or a higher dimensional subspace showing up. But this is the general solution in standard form. Those of you who have seen some differential equations, or who shall see some differential equations, this is analogous in differential equations to having, what do we notice here? This is what is called a particular solution. And this, if I didn't have this vector, what would this vector and its multiples satisfy? What equation would it satisfy? What do you get if you multiply A, my original matrix? Where was he? 1, 1, 3, 1, -1, -1, 2, 0, 2. What do I get if I multiply it by the vector -1, -2, 1?
Should be the same. Shouldn't it be 0?
-1 minus 3 plus 3 is 0. -1 plus 2 minus 1 is 0. -2 plus 2 is 0. Well, that shouldn't surprise you, because throwing away the constants would have corresponded to just putting zeros for the constants and solving the same equation. So you've got a solution of the homogeneous equation. For future reference, what's a geometric interpretation of saying So this is an important comment. This is going to be something that comes up lots in this chapter. What is the geometric interpretation of this vector from knowing that it solves Ax equals 0? How does
Perpendicular to all the rest.
when I'm multiplying here, yes, we can think of linear combinations of columns. We'll do that soon. But instead, think about what's going on with the rows. Each of the rows is what to this vector? Orthogonal. That's what this says, right? So the solution to this system of equations is giving me an x that's orthogonal to the rows of A.
So are two of them parallel then?
Two of whom?
The rows in the matrix.
No, they're not. But there's, okay, I'll get back to that. Cal?
Where did you get the matrix A that you used in that last step from?
Just the, here,
It's not augmented.
Oh, you just took out the, okay, I got you.
the original matrix.
Got you. Okay.
So x is perpendicular to all the rows. Therefore, by homework you did week 2, it's orthogonal to any vector in the span of the rows. Remember that problem? So it's in the perp of the span of the row vectors. But geometrically, this is really cool because this is a way to find a vector that's orthogonal to a bunch of vectors. And we'll do more with this later in this chapter. Now, I actually want to come back to Bryce's comment / question. What is this saying about the original 3 row vectors? The fact that we ended up with this row of zeros. So I'm going to, for the moment, ignore the B vector and just talk about the homogeneous equation here. So if we just looked at Ax equals 0, and we're saying in this case we have 3 row vectors, so we're getting 3 equations. And what's the interpretation of the rows of the matrix? They're what? For these, if you think of these as equations of the coefficients, but what is this set? If I take a vector in R3 and I look at all the vectors orthogonal to it, it's a plane. And what's this? What's the word we've been using? The normal vector of the plane. So what we're having here is 3 planes, and we're looking for their common intersection when we're trying to solve the system of equations. So one of the equations is a plane. And the geometric interpretation here would be that A1 is a normal vector to that plane. Agreed? I don't want to put it in this picture because the picture will get too cluttered if I have. Now you have your second equation. Okay, let's just say your second equation gives you a plane that looks like this. So let's say the second vector looks something like that. So far the intersection of the 2 planes is a line. Agreed? What is it meaning that the third equation was redundant, that we ended up with a 3rd row of zeros?
They share the same plane.
Yeah, the third one would intersect to that line.
It has the
Both
same
sides.
normal vector.
Oh, okay. I see.
No, we don't have the same plane. Look at the equations. Those 3 vectors are not all repeating. But what's true about A3?
It intersects both the other planes and act out.
They can be spanned
It's
by-
also
Okay, the plane, the third plane, if I put it in this picture, is going to intersect in the same line that we already have.
Is it gonna be a linear combination with A1?
So what's that saying about the normal vector to the third plane?
It's A2.
It's a linear combination.
Oh, it's
It's a linear combination of these. It's in the same, it's in the plane that these two normal vectors span. The third vector is a linear combination of them. Which is saying that you can think of this as a pivoting door that pivots on a hinge. Like the axis of this door here is vertical, right? All the positions of these planes, all of those planes pass through the vertical axis here. So if I take any three planes that pivot on this same line, I'm going to have three equations that are redundant because I only need two of them to determine that line. So the third equation, you know, might be some plane in the middle here. But it's not giving me any new information. And that's equivalent to saying that it lies as a linear combination of the two normal vectors. And that's what the linear algebra told you here with the matrices. Yes, sir?
Couldn't you kind of know that directly from like the thing, instead of having to do the whole plane interpretation? If you just take x as the normal vector of the plane, like with a1.x equals 0, a2.x equals 0, a3.x equals 0. Like if that's true, then x is like the normal vector of the plane containing all three, and therefore all three are in the same plane.
Because there's a non-zero vector x.
Yeah.
Yes, exactly right. Right, so what Matthias just said was a solution of the original system of equations is a vector that's orthogonal to all these guys.
Which is only possible if you're lying.
And since we have a non-zero solution, that determines a plane by looking at the things orthogonal to it. Therefore, these all lay in a plane. Correct.
So if we didn't have one that was, if the third one was
If I had a
not,
third pivot,
right, then you just have one point, right?
Or no solution.
so I would have a unique, I would have the origin as the solution to the homogeneous equation, but imagine what would have happened if we had gotten to this point and this had not turned into a zero.
Then you'd have no
Then I'd have no solutions, and that would be called inconsistent, and we're going to talk more about that on Monday. Okay, so we're going to, on Monday, we'll talk exactly about that question, but let me give you the definition anyway, before I do number 10. So we say the linear system, the system of linear equations or linear system is consistent if it has some solution, but if it has no solution, it's called inconsistent. There's the in again. And so you can already see from what we've done today that you're going to detect an inconsistent system if the right hand, the augmented part, ends up with a pivot in it. A non-zero entry where there was a zeros all the way on the left.
But if the last one's not a zero, if the it's not 3 zeros, right?
Well, if you don't have 3 zeros here, then you have
A 1, and then you just have one.
then you have 3 pivots and a unique solution, no
One
matter
unique
what.
solution, right?
But if you have 3 zeros here, that means you have redundancy. But if you don't have a zero there, that means you have a contradiction because it's
Right.
saying 0x1 plus 0x2 plus 0x3 is 5. There aren't too many real numbers x1, x2, x3 to do that. Okay. So on Monday we'll talk about the theoretical framework of all this. But I want to do one more example here, just to there's a moral lesson from that. So suppose, Rebecca, if I missed something good,
Oh, yeah.
I can ask you.
Wow. I speak for everyone.
Really?
I speak for the trees.
So 2, 1, 4, negative 1, 5, 3, negative 1, 1, negative 4, 0, 5, 2, 9, negative 3, 11.
Wait, okay.
Let's double check that I did not miscopy something. What are you going to do with this? You could cry.
Square both sides.
My kingdom for a 1.
Get a 1 in the upper left-hand corner.
Yeah, you could subtract the first row from subtract the second row of, subtract the first row from the second row.
Switch the second row and the first row, and then subtract the second row
Yeah.
from the first row.
So
Do what you want, put you want.
you could say, without using your intelligent mind, you could just multiply through by a half
Yeah.
and then have a 1. But then you're going to be stuck with fractions. So the moral of the story is, if it's possible, see if there's some combination of the rows you can take that will give you a 1. And if you learn a little bit of abstract algebra or number theory, you know that as long as 2 of these numbers are relatively prime, you can always do that. If these were both multiples of 2, there's no combination I can ever take that's going to give me a 1. But as long as some pair of these numbers are not multiples of a common number, as long as they're just multiples of 1, that's what relatively prime means, then you can always take some multiple of 1 plus some multiple of the other that will give you a 1. So be on the lookout for that. And you guys are telling me that, in fact, if I take middle row minus the second and put that up here, I would have 1, negative 2, negative 3, negative 3, negative 5, and then I could just go ahead and put my other rows in there. So I've done a switch and a
I think it's just
addition
5.
of a multiple.
Subtract that.
Okay, so let's quickly go through this, because I want us to see a phenomenon now. Let's hope it works, and that the person who prepared this didn't screw it up.
That'd be unfortunate.
Dastardly person. So what do I get? Recopying the first row, you guys can tell me what to write for the second row now.
2 times
Right.
0, 5, 10, 6. No.
It's probably going to be a multiple of 5.
If you trust me that for all the problems on WebWork except the ones that are solving some sort of applied problem, which will show up in a few weeks, you should, if you get something like this one, one of the numbers isn't divisible by 5, you've made a mistake. Go back and check. Don't keep going. All right, last row. Oh, this is getting hard. 15 plus 9.
24,
12.
15, yeah.
36. How convenient.
And now you say to yourself, let's divide through and make things nice and simple. So I get 0, 1, 2, 1, 3.
0, 1, 2, 1,
Did I screw up?
3.
No, it's just.
0, 1, 2, 1. Oh no, again. So the last row is going to turn into a row of zeros again. And what does the first row do when I now try to put it in reduced echelon form? Again, I've got my pivots here. So I want to add twice the second row to the first. I get 1, 0, 1, negative 1, 1. Okay. So I just wanted to show you an example where we can write down the general solution in standard form. What are you gonna have now? How many free variables, folks?
Two.
2. So, again, I'm saying take the equations, solve for everybody, solve for the pivot variables. So what do you get? If you wrote this equation down, it would be x1 plus x3 minus x4 equals 1. So you're going to have 1 minus x3 plus x4. You guys following me? Because I'm running a little short on time, I'm not writing every step. x2 is going to be what? 3
And minus 2 is 3. Minus
minus
x4.
x4. And x3 is x3 and x4 is x4. Include those or else you're going to mess stuff up. So the general solution is going to be, you have vectors here, nicely lined up. You have your vector of scalars plus a free variable for x3, a free variable for x4, and their respective coefficient vectors are -1, -2, 1, 0, and 1, -1, 0, 1. That's the general solution. Okay?
Yeah.
You can have an extra minute on me.